Friction is both problematic and useful in many applications. So whenever there are some moving parts like in IC engine, piston and cylinder, they have relative motion, similarly journal and bearings. So in that case, we want less friction so that we have less losses. Although friction is also useful in many applications, like it is helpful for you in the walking process. When you walk, then you need friction. It is very difficult to walk on a slippery surface. Then when you are writing on the board with the help of a chalk, then again friction is useful. Then for braking purposes, then if you want to pull some water from the well, and for placing a ladder against a wall. So these are some of the applications where friction is useful. Now let us introduce. In previous chapters of mechanics, we assumed that the surfaces were either frictionless or rough. Okay. So when the surfaces are frictionless, surface could move freely with respect to each other, and when they are rough, tangential forces prevent relative motion between surfaces. Now actually no perfectly frictionless surface exists. So however smooth the surface may be, it has some friction. For two surfaces in contact, tangential forces are called as friction, and they will develop when one attempts to move one surface relative to another. Now the frictional forces are limited in magnitude and will not prevent motion if sufficiently large forces are applied. So whenever you apply some small force, then your body will not move. Or when you apply large forces, then body starts to move. So frictional forces, they cannot prevent motion. Now the distinction between frictionless and rough is therefore a matter of degree. Okay. So if the force is very large, so you can say that the surface is frictionless, and if you are applying very small force, then for the same surface you can say that this surface is rough. Now there are two types of friction: dry, which is also called as Coulomb friction, and fluid friction. Now fluid friction applies to lubricated mechanism, because in many applications in engineering you are doing lubrication. Okay, so there you are using fluid friction. Now the present discussion is limited to dry friction. So in our course of mechanics, we will only deal with dry friction. We will discuss laws of dry friction. So as you can see, suppose this block is placed on the surface, so we will have two forces. One force is in the downward direction because of the weight, and another is the reaction of the surface. Now if you apply some force on the block in the horizontal direction, okay, but suppose that force is small, so that this block will not move, so it means that there must be some opposite force to this F, so that this block is not moving, and that force is the force of static friction. Okay, now if you continue to increase this force will also increase, frictional force will also increase, but a point is reached when this force will become maximum, and then this block will just start to move. Okay, so this maximum force, this is called as the static friction, and when this block just start to move, then this force is called as kinematic friction. Okay, and this kinematic friction force is slightly less than the maximum static friction force. So maximum static friction force is Fm is equal to mu s into n, while this kinematic friction force is equals to mu k into n, where the value of mu k is slightly less than mu s. And there's mu s and mu k, they are also called as coefficients of friction. So this is how this friction force works. Now this in this table, some of the coefficients of friction values are shown. So suppose metal is placed on metal, then this value of mu s varies from 0.15 to zero point 0.6. Similarly, if metal is placed on wood, then this value is 0.2 to zero point 0.6. Similarly, you can see other values. So for example, if rubber is placed on concrete, then this value is very high, and it is varies from zero point 0.6 to 0.9. Okay. And as we know, this kinetic friction force is slightly lower than the static friction. So approximately it is around 75% of the static friction force. Now maximum static friction force and kinetic friction force are proportional to normal force. So from this law you can say that these forces are proportional to the normal reaction force. Okay. And they depend on type and condition of contact surfaces, because this value of mu s, it changes with the surface. Okay, so there are two variables, n and mu s. So the frictional force will depend on the reaction and the two surfaces which are in contact, while it is independent of the contact area, because in this equation there is no term related to area. So we can say that the frictional force is independent of the contact area. Now there are four situations that can occur when a rigid body is in contact with a horizontal surface. So let us see those four conditions. So this is the first condition, when this force is applied from the top. Okay, so in this case we have the weight, we have the normal force, and since it is applied from the top and block cannot move in the bottom direction because of this restrain. Okay, so we can say that in that case frictional force is zero. Now second condition is that when this force is applied at certain angle. Okay, now we can reduce this force in two components, px and py, and in that case there will be some frictional force, and suppose there is no motion, then this px will be less than f, because f will be equals to px and f is less than mu s by n. Now n is equal to py plus w, because this one component will act with w to counter this n. Okay, so n will be equals to py plus w. Now the third condition is that motion is impending, means motion is just about to start. Okay, so that we call it motion is impending. Okay, in that case this fx will be equals to fm. And the fourth condition is the motion, when this force is such that it imparts motion to this block. So in that case px is greater than the frictional force. So when there is no motion, then px is less than the frictional force. When motion is just about to start, then the applied force is equal to the frictional force, and when the motion is started, then applied force is greater than the frictional force. Angles of friction. So sometimes it is convenient to replace normal force and the frictional force by their resultant. Okay, so this is the first case. In this we have no friction, so the resultant force will be equals to the normal force. Now in the second case, we can represent the normal force N and this frictional force F by their resultant R, and this is the angle between the normal and resultant force, and this is the angle is the phi. Okay. Similarly, in the third case, when the motion is impending, then again we can find the resultant R, and in that case we call this phi is equal to phi s, and this is the angle of static friction. Okay, and you can find by using the tan law, tan phi s will be equals to Fm by n, which is equals to mu s n by n, and so tan phi s will be equals to mu s. Okay, so that's coefficient of static friction we can find by taking the value of tangent of this angle. Similarly, when motion starts, then we call this angle phi is equal to phi k, and this tan phi k will be equals to mu k. Now, to better understand this angle of friction, consider a weight resting on board with variable inclination theta. So this is a weight, and this is resting on this board, and this board has a variable inclination. So suppose initially it has inclination 0, so in that case there will be no friction. Now suppose we move this board like this, we are changing the inclination of this board. So initially what happens, there will be no motion. Okay, now what we can do, we can break the forces in the components. So this force is W sine theta, this force is W cos theta. Okay, similarly we have n will be equals to W cos theta because this will balance, and F will be equals to W sine theta. Now at one point what happens, if you continue to increase this angle, that at one point what happens, the motion is about to start. Okay, so means motion is impending. Okay, so in that case we call angle this theta equal to theta as the angle of repose. Okay, and this is equals to phi r, which is the angle of friction. And when the motion starts, then this theta will be greater than theta s. Okay, so when your this theta means the angle of inclination of this board is greater than theta s, then this motion will start. To solve the problems involving dry friction, so sometimes you have this type of case where all applied forces are known, coefficient of static friction is also known, and you have to determine whether body will remain at rest or slide. Okay, so sometimes you have to solve these type of problems. Then another case might be all applied forces are known and motion is about to start, motion is impending, and you have to determine the value of coefficient of static friction, that is you need to find the mu s. So in that case, first case, you need to calculate the frictional force. Okay, in the second case you need to calculate the mu s, and in the third case the body is moving, so coefficient of static friction is known, motion is impending, and you have to determine magnitude or direction of one of the applied forces. So you may need to find the direction of P, magnitude of P, or any other applied force. So this is how you can solve the problems involving dry friction. One sample problem. So consider this block on this inclined plane, and in this block 100-pound force is applied. The coefficients are given, mu s is equals to 0.25 and mu k is equal to 0.2. Now we have to determine whether the block is in equilibrium. and find the value of frictional force. So these are the steps. First we will draw the free body diagram. Okay, and remember that the friction force is opposite to the direction of impending motion. So in whichever direction you uh, know that the block will move, so then you will apply the force, frictional force in the opposite of that. Then next step is to determine values of friction force and normal reaction force from plane required to maintain equilibrium. So we will suppose that suppose the body is in equilibrium, and then we will calculate the frictional forces and normal reaction required for equilibrium. And what we will do next, we will calculate the maximum friction force. Maximum friction force can be calculated from Fs is equal to mu s into n. Okay, so we will calculate the maximum friction force. Okay, so if it is greater, block will not slide. So friction force is greater, then block will not slide. And if maximum friction force is less than the friction force required for equilibrium, block will slide. Okay, so we will calculate the forces for maintaining equilibrium, and we will calculate the maximum frictional force. So if maximum friction force is less than the friction force for equilibrium, then block will slide, otherwise it will not. So let us solve the problem. So this is the free body diagram of the problem. So this weight will act vertically downward, and n is normal to the surface, and this is the applied force. And suppose because force is applied in this direction, so we are supposing that the motion will be in this direction, so the frictional force will be opposite to this, so the friction force will be in this direction. Okay, so now suppose we are supposing the equilibrium, then for equilibrium summation of fx will be 0, summation of fy will be 0. So suppose this is our x direction. Okay, so in the x direction we have this force, applied force, then we have one component of this weight, and then we have the friction force. So from friction force, from this we can find F is minus 80 pound. Okay, similarly we can calculate Fy. So in the y direction, which is this direction, okay, this one, so we have n, then we have one component of this weight, so n minus 4 by 5 of 300 pound, so n will be equals to 240 pound. So these are the conditions for equilibrium. Okay, now sign means that this force is opposite. Okay, now we can calculate the maximum frictional force with this formula. Okay, so now we know the n and mu s is given in the problem, so Fm is the 60 pound. Okay, so now your maximum frictional force is less than this force, so that means the block will move. Okay, because this force is less than the force, so that means the block will slide down the plane. Okay, so now if maximum friction force is less than the friction force required for equilibrium, block will slide. So actually now since block is sliding, okay, so now the frictional force will not be equals to the maximum friction force, but it will be equals to the kinetic friction. Okay, so we need to calculate the kinetic friction. So kinetic friction will be equals to Fk is equal to mu k into n, and Fk is 0.2 given in the problem. 240 No. So actual friction force will be 48 pound. Okay. So this is how you can solve the problems involving friction. First we will learn wedges. So they are simple machines. So this is wedge C and D. They are forming a wedge. Okay. So these are the simple machines that can be used to lift the weights. And in these machines, force required to lift the blocks are significantly less than its weight. Okay. And the friction force prevents wedge from sliding out. It will not slide out because of the friction force. And we want to find the force value of this force that is required to raise the weight. For that, what we do, we will first draw the free body diagram of this body. So in this body, we have the force of weight. Now, since when we apply this force, this block will move in the upward direction. So we will have the frictional force towards the downward direction. F1 is equal to mu s n1. And also we have one normal force. Okay. Similarly, we have a normal force at this horizontal surface plus this block will try to move in this direction. Okay, so frictional force will be opposite, so another friction force will be F2 is equal to mu s n2. Now what we can do, we can for equilibrium we can equate the fx is equal to 0, fy is equal to 0. So in the x direction we have minus n1 plus mu s n2 will be equals to 0, and in the y direction we have minus w minus mu s n1 plus n2 is equal to 0. Or we can also write in the form of resultant. So we can find r2, we can find r1, and we can write in the vector form r1 plus r2 plus w should be equals to 0. Similarly, we can draw the free body diagram of this wedge. So in which this wedge we have this force F. Now there are the reaction forces which will act on the top portion. So here we have N2. So here we have minus N2. Similarly, here we have F2. So we have a reaction force minus F2. And now these are the frictional forces which will act towards the bottom side of the wedge. So we have one normal force N3 which is normal to this surface. Okay, so this is normal to this surface. And similarly, since we are applying a force in this direction, so we have some opposite frictional force F3 which will be equals to mu s n3. Okay, so again we do the same thing. We can have fx is equal to 0, summation of fx is equal to 0. That will give us mu s n2 because this is in the x direction. Now there is some inclination of because we have 6 degree of angle, so this n3 is bit inclined. Okay, so we will be having a some angle here. Okay, so we will have some components, so we can write that. So we have n3 mu s cos 6 plus sin 6. Okay, and plus p, that will be in x direction. Okay, similarly in the y direction we have minus n2 plus n3 cos 6 minus mu s sin 6. So we can find the components of both the forces in the x and y directions, and we can also write in the form of a vector. So we have p r2, the resultant of these forces are r2. Similarly, the resultant of these forces is r3. So p minus r2 plus r3 is equal to 0. So this is how we can deal with the wedges. Example of friction is the self-threaded screws. This is the figure of self-threaded screws, and these square threaded screws, they are frequently used in jacks, presses, etc. And their analysis can be performed similar to the block on an inclined plane. Okay, and we are using the principle that friction force does not depend on area of contact. So we have represented this screw with this plane. Okay, so one of the thread of the base has been unwrapped and it is shown as a straight line that is equal to 2 pi r, and the distance which is moved in one rotation, which is equals to L, is shown in vertical. Okay, and this is the weight W, and we have shown the this force Q, which is equals to the force P that is necessary for lifting any weight. If you want to lift any weight, then you will apply force P. So this force Q is such that the moment of force Q is equal to the moment of force P. That is, Q should be equals to P into A divided by R. Okay. So if we calculate Q, then this force Q will be equal to P. Okay. Now there is a one case which is also called as self-locking case. So that case will occur when this angle theta s is greater than the angle theta. So in that case, what happens if you put some weight on this uh, screw or on this jack, so it will not move downwards. So that means that it is self-locking. Okay. So in that case, we have to apply force to lower the weight. Okay. So this condition will occur when this angle phi s is greater than theta. Okay. Then you need to solve for Q to lower the load. And then there is another case in which when you put on the load, so it will automatically try to unwind and lower the load. So in that case, you have to apply the force in the opposite direction so that the weight do not come downward. So that will occur when phi s, means the angle between the resultant and normal, is less than the angle, this angle theta. Okay, in that case you have to solve for the force Q to hold this weight so that it will not come down automatically. So this is how we can solve the problems that are related with the square threaded screws that are frequently used in jacks and presses. Now we will solve this problem related to square threaded screws. So as you can see in this figure, a clamp is used to hold two pieces of wood together. So these are the two pieces of wood as shown, and this is the clamp, and this clamp has a double square thread of mean diameter 10 millimeter, and the pitch of this thread is 2 millimeter. Okay. The coefficient of friction between threads is 0.3. Now if a maximum torque of 40 Newton meter is applied in tightening the clamp, determine the force exerted on the piece of the wood. And in the second part, the torque required to loosen the clamp. So this is the problem. First we will calculate the lead angle and pitch angle, and then by block and plane analogy as discussed, with impending motion up the plane, calculate the clamping force with a force triangle. So we will make a force triangle and we will calculate the clamping force. And then with impending motion down the plane, we will calculate the force required to loosen the. Now we have made this diagram. So in this diagram, this is the weight W, And first we are considering the up, means suppose we are tightening the screw, so for that we need to uh, up force, means the force which is applied in the up direction. So now for calculating the lead and pitch angle for double threaded screw, the lead is equal to twice the pitch. Okay, so pitch is given 2 mm, so we will take lead as 4 mm. So this L is equal to 4 mm, and this length in the horizontal direction will be 2 pi r, as we have already discussed. So that will be 10 pi because r is 5. So from the figure you can see that tan theta will be equals to L divided by 2 pi r. So from that you can calculate the lead angle. Lead angle is when you take the inverse of this, the lead angle will be 7.3 degree, and this angle for static friction tan phi s will be equal to mu s, and it is given as zero point 0.3 already in the problem. So then this phi s will be 16.7 degree. Okay, now block and plane analogy with impending motion will be like this. So we will make the force triangle. So W is downward, Q is on the right side, and then R will complete the triangle. So now this QR is 40 Newton meter. It is already given in the problem. So R you know, then from this you can calculate Q. That will comes out to be 8 kilonewton, and now this angle is 24 degree. So because this is 7.3 and 16.7, when you add this, that will become 24. So now the tan theta plus phi s will be Q by W. So you can calculate W, which comes out to be 17.97 kilometer. Sorry, kilonewton. Now for calculating the force to loosen up the screw, now this time we assume the Q in this direction because you need Q in this direction to loosen. So again we will make the force triangle. So W, and this time Q will be in this direction and R will be in this direction. So now tan phi s minus theta will be Q by W, and then Q comes out to be 2.975 kilonewton, and torque you can calculate by multiplying the R. That will be equals to 14.87 Newton meter. So as you can see, this is considerably lower. While tightening the screw, you need 8 kilonewton. While you're loosening, we only need 2.975 kilonewton. So the force required is different for tightening and loosening the screw. So suppose pulley, and this is a belt passing through the pulley. So we will discuss what will be the frictional force that will act when this belt is about to slide. So suppose the tension here is T1 and tension here is T2, and these P1 and P2 are the points of tangential contact between the belt and pulley. So first thing we will do is to make the free body diagram of the element. So we will consider this element, this element, and the free body diagram of this element has been drawn here. So as you can see, suppose here on the left side we are having a tension force of T, and suppose on the right side we are having a tension force T plus delta T, and this reaction force will be in the vertical direction delta n, and this frictional force will be from the law of static friction mu s delta n. Okay, So this is the free body diagram. Now from the free body diagram, summation of fx will be equal to 0. So in the x direction we have t plus delta t cos theta by 2. So this angle is theta by 2 and the component of this force will be here like this. Okay. Similarly, we have minus t cos theta by 2 and minus this is the frictional force which is also in the x direction. Similarly, you can write for y delta n. This is the force and we will have two components. One is this and another is here. So our equation becomes this. Okay. Now what we can do, we can suppose we can solve for delta n from equation this and we can put in the second equation, then finally you will obtain this equation divide and when you further divide by delta t, then this is your final equation. So delta t by delta theta cos delta theta by 2 minus mu s t plus del t by 2 into sine del theta by 2 divided by del theta by 2. Okay. Now when suppose if delta theta is very small, then this term becomes 1 because cos 0 is 1. So when delta theta approaches 0, this term becomes d t by d theta, and also you can also neglect delta t because as delta theta approaches 0, so this delta t will also be negligible. So this will be 0 and for small values this sine del theta by 2 will be approximately equal to del theta by 2 and which will cancel out. So finally we get this equation dt by d theta minus mu s t. So this is a differential equation. You can easily solve this by using the variable separable method, and you can integrate it from theta is equal to 0, theta is equal to beta. Because your angle is changing, maximum angle is this beta and minimum possible angle is 0. So when you solve this equation, the solution will be ln t2 by t1 is equal to mu s beta, and we can also write t2 by t1 is equal to e mu s beta. So this is the solution of this equation, and this is equation governs the belt friction. Okay. One problem related to belt. So here you can see a flat belt connects pulley A to pulley B. So this is the pulley A and this is the pulley B, and this belt connects both the pulleys. The coefficient of friction are mu s is equal to 0.25, static friction and kinetic friction is 0.20 between both pulleys, knowing that the maximum allowable tension is 600 pound. So maximum allowable tension is this. Determine the largest torque which can be exerted by the belt on pulley. So this is our problem. How we are going to solve this? So this is the strategy. The key to solving this problem is to identify the pulley where slippage would first occur. First, by our knowledge, we should identify on which pulley slippage can occur, and then find the corresponding belt tensions when the slippage is impending, as we have done in the previous equation. The resistance to slippage depends upon the angle of contact beta as well as upon the coefficient of static frictions. Now this mu is same for both the pulleys. Slippage occurs first on pulley B, for which beta is smaller. So the chances of slippage will be more on smaller pulley. So now let us solve this problem. Diagram on the first pulley as we done during the derivation. So this is T1, T2 is given maximum 600 pound, and this is the solution which we have already obtained. T2 by T1 is equal to E mu s beta. So from this we can obtain T1 as 355.4 pound. Now let us make the balance on bigger pulley. So this is the free body diagram of the big pulley. So by summing the moments about A, we have MA, and we will have the moments because of these two tension forces, T1 and T2, and this 8-inch is the diameter of the pulley. So MA plus 8, and this is the resultant of the these tension forces. So finally the moment comes out to be 163.1 pound foot. Now from the solution we can check that the belt does not slip on pulley A. Can also check it by computing the value of mu s required to prevent the slipping at A, and then verifying it with the value of mu s. Okay, so now applying this equation for second pulley, mu s beta, and this. So this comes out to be 0.524 mu s beta. Now this beta for bigger pulley is 240 degree, which is 4 pi by 3 newtons. So from this we can calculate mu s, and mu s comes out to be 0.125, which is much smaller than the frictional force, maximum friction, 0.25. So we can say that the slippage would not occur on the pulley A. So this is the first problem related to friction. So the problem is determine whether the block shown is in equilibrium and find the magnitude and direction of the friction force. So we have to find out whether this block is in equilibrium, and we have to find the magnitude and direction of the friction force when this angle theta is equal to 25 degree and this applied force is equal to 725 Newton. So let us solve this problem. First of all, we have to draw the free body diagram. So suppose this is your body, okay. So I will make the block, and so this is your block, suppose. And let us consider the x-axis in this direction, and y direction, y-axis is in the normal direction to this plane. Okay, so this is our y-axis, this is our x-axis, and the forces which are acting are the weight force, and this is equal to 1.25 kilonewton. Then this force is acting P, which is 750 Newton, and normal force will act perpendicular to this N, okay, normal force. And suppose this force P, this pushes the block in this direction, so the frictional force will act in the opposite, means to resist the motion. So this will be the frictional force. Okay, now we can resolve these forces into the x and y directions. This force W and this force P. So for that we need the angles. So this angle is given theta, which is equals to 25 degree. Okay, so we have suppose this is the perpendicular, this is the y direction, okay, and we have this is the perpendicular, okay. So this is this line is perpendicular to this line, and this line is perpendicular to horizontal, okay. So this angle will be theta. Similarly, you can find for this. So this is the horizontal, okay. So in the y direction, let us draw this. So again, this angle will be theta, okay. So according to equilibrium, summation of fx will be 0 and summation of fy will be 0. Now in the x direction we have w sine theta, then this and this will be here, okay, and this p force will act in the opposite direction, so we can say minus 750 cos theta, and frictional force, okay, F will be equal to 0. And similarly in the y direction we will be having W cos theta, which is downward, minus n, and we have the one component this plus 750 sine theta equals to 0. So we just need to solve the two equations, then we will get F as 172.6 Newton, and n you can calculate from the second equation, that will be comes out to be 1404.5 Newton, okay. And maximum frictional force maximum will be equal to mu s into n, which will equal to, now mu s is 0.35 given here into 1404.5. So maximum friction force is friction. So this is our problem. There are two blocks and they are attached with a cable, and this force is applied. So we are given coefficients of friction, static as well as kinetic, and we have to determine the force P required to start the motion of this 30 kg block, okay, when this cable is attached, and the second part when this cable is removed, okay. So let us start. So first we will do the first part A. So let us make the free body diagram, okay. So first we will make the free body diagram of 20 kg block. So in this we have W, then we have a force of tension, then suppose this block will move in this direction, then we have friction force here, and we have a normal force, okay. Now according to equilibrium, W will be equal to N, which will be equals to 20 into 9.81, which will be equal to 196 point 196.2 Newton. Okay, 0.2 Newton. Similarly, we can equate this is summation Fy, and summation of Fx should also be 0. That means this T should be equal to F. Okay. Now F we can calculate. F will be equal to mu S into N, and mu S is 0.4 while N is 196.2. Okay. So that comes out to be 78.48. 78.48 Newton, and thus we will get T is equal to 78.48 Newton. Okay. Now we'll draw the free body diagram for block 2. So in this we have a reaction force which is equal and opposite to this. Then there is a friction force F which is equal and opposite to this force. Okay. Now we have weight of this block. Okay. Then we have a tension force here. We have P here. Okay. And another friction force, let's say F2 will be here. Okay. And then we have a normal reaction force N2. So again we will make the equilibrium condition. So summation of Fy is equal to 0. So in the F we will be having a weight plus N, that should be equals to N2. Okay. So weight is equal to 30 into 9.81 plus we know this N 196.2. So this will be equals to N2. So it comes out to be N2 will be equal to 490.5 Newton. Okay, 490.5 Newton. Similarly, we can equate the summation of Fx in the x direction, though that should also be equal to 0. So this P force should be equal to T plus F and plus F2. Okay. So this T we have calculated 78.48. F we have calculated again 78.48, and this F2 will be equal to mu S N2. Mu S N2. So mu S we know 0.4, and N2 we know 490.5. So from this we can solve for P, and it comes out to be 353.2 Newton. 353.2 Newton. So this is the smallest force which is required for the motion of block B when the cable is attached. Okay. Now second part is a little simpler one, B part. Okay. So let us solve the B part here. Okay. So free body diagram. So when this cable is detached, then this will act as a single body. So free body diagram will be like this. You will be having both the blocks moving together. Okay. So we have a vertically downward force of W, then a reaction force N, and suppose this is moving in this direction P, so we have a friction force here. So these are the two forces. Okay, now W will be equals to means total of this, so 50 into 9.81, that comes out to be 490.5 Newton. Okay, and then P minus F will be equal to 0 in the x direction, so P will be equal to F, which is equals to mu s into n, that will be equal to zero point 0.4 into 490.5, and when we solve it, so it comes out to be 196.2 Newton. Welcome dear students. So this is problem of friction. So the problem is knowing that the coefficient of static friction between the collar, so this is the collar C, and the rod is 0.35. Determine the range of values of P. So this is the applied force P. So we have to find out the range of values of P for which equilibrium is maintained when this angle theta is equal to 50 degree and M, this applied couple, is 20 Newton per meter. So now let us solve this problem. So solution, I am writing solution. So first I will draw the free body diagram of this rod AB. So this is the rod AB. So in this rod we will be having reactions here. So you can call it AX, AY, and then we have a force here. Sorry, yes. So this force we will have, and the direction of this force is this. Okay, so let us call it FBC. Okay, so what we can do for equilibrium, we can take the moment about A, and it should be equal to 0. So then we have M, and we can break this force FBC into two components. One component will be here and one component will be here. So the moment, because of this vertical component, will be 0, so we will have only this, and this moment is opposite to this, so we can write it minus FBC cos theta is equal to 0. Okay, so now this is 20 FBC and this is 50 degree equal to 0, and this will give us FBC. So the value of FBC comes out to be 311.45 Newton. Okay. Now second thing we will make the free body diagram of collar C. Now there are two conditions. One condition can be motion impending upward and motion impending downward. So let us consider first case, motion impending downward. Okay, so we have this force P, Then if motion is impending downward, then friction force will act here, and this friction force will be mu s into n, and we will be having n normal, and then we have this force F VC, and this angle is 50 degree. 50. So now we have all the forces that are acting on the collar. So we can have for equilibrium summation of Fx is equal to 0. That means F BC cos 50 degree minus n will be equal to 0. So from this we can get n. So the value of n comes out to be 200 Newton. Then we have summation of Fy is equal to 0. So in the y direction we have P acting downward, then FBC sine 50 degree. So the component of this force, okay, and minus frictional force. This is the frictional force F. So we can directly write it. So just a minute. So mu s is given as 0.35, so mu s into n, which is we already get 200 equal to 0. So from this we know the value of this FBC. So we can get the value of P, which comes out to be 168.35 Newton. Now second scenario can be when this collar is impending upward, okay. So FBD of collar C, motion impending upward. So again the diagram will remain same. So here we will have FBC is 50 degree, FBC, then we have P, and friction force will again will act downward. So this is the friction force, again mu s n, and here we will have n, okay. So again summation of Fx is equal to 0, summation of Fy is equal to 0. So this equation will remain same. Now in the y we have P minus FBC sine 50 degree, and this time this will be plus 0.35 into 200 into 0, and this from this we can get P is equal to, the value of P comes out to be 308.35 Newton. So we have to find the range of P for which this is in equilibrium. So P will be in this range, 168.35, and then P, then 308.35. So this is the final answer. We will write in this range. So this is how we can. Welcome dear students. So now we will solve another problem related to friction, and this problem is related to wedges. So the problem is two wedges of 10 degree and negligible weight are used to move and position this block, okay. knowing that the coefficient of static friction is 0.25 at all surfaces of contact. Determine the smallest force P that should be applied as shown to one of the wedges. So we have to find the value of P. So let us solve the problem. So first we will calculate phi s, and that will be equals to tan of 20.25 and it comes out to be 14.04 degree. Okay, now next we will draw the free body diagram of block. So suppose we are drawing it here. Okay, so first force is the weight of this block, then we have N, normal reaction. Okay, and then we have the friction force, suppose F1, then we have the normal reaction here, so you can call it N2, and friction force here. Now you can replace these forces by the resultant, so we can have R1 and this angle is phi s. Similarly you will have R2, the resultant of F2, and this angle is again phi s. Okay, now what we can do if the block is in equilibrium, then all these three forces should form a force triangle. So we can make a force triangle and then we can apply the sine law. Okay, so this is the force triangle, so therefore this is the W. Then we are having R1 and R2. So suppose this is R1 and then this should close this R2. Okay, now this angle we know phi s, and this angle is known to us. This is again phi s. So we need to find the other angles also. So this angle will be 90 degree minus 2 times of phi s. So this is just a geometry, you can work out it, it's not a big problem. So this comes out to be 61.9, and then you can apply the triangle law, so you can find this angle also. So this angle will be 90 plus phi s, because up to this we are having 90, okay, and this phi s is plus, so this angle will be 104, okay, 0.0. And this angle we have calculated by using triangle law. Now we can apply sine law. So by using sine law, we can have W upon sine of 61 degree, 61.92, okay, 61.9 this value, and then we can have R2, R2 upon 104. So sine of just a minute, sine of 104.4 degree, sorry, 04. So from that you can calculate R2, and it's come out to be 43439.8 pound. Okay. Now next step we will draw the free body diagram. Free body diagram of wedge. So this is your wedge. Okay, so we will have R2 on top. We will have R2. Okay, then we have a P, and we will have R3 here. So I'm not showing the friction forces separately this time. So we will have R3, and this angle is 14 degree, right? And this angle we have 10, because the wedge angle is 10, so 10 plus phi s. Okay, now what we can do, we can make a forced triangle for this. So suppose P is here, then we can have R2 here, and then this should be R3. And the angle comes out to be so we need to find these angles. So this angle will be means 14 plus 10 plus 14, so 28 means this angle is around 14.04 plus 24.04, so around 38.08 degree. So this angle will be this, and we need to find other angles also. So this angle will be 90 degree. So 90 degree minus of 24.04. Okay. Now we can apply sine law in this triangle also. So from the sine law we get P upon sine of this 38.08, and that will be equals to R2 upon, because we have already calculated R2, So R2 upon sine of this 90 minus 24. So from this, since we know R2, this is the R2, so we can calculate P, and the value of P comes out to be 297.297 pounds. So this is the